Good morning. I would like to thank organizing committee, and at the same time, my talk will be based on building better quantum optoelectronic device from atoms up, and by having Professor Muru as the first speaker on lasers. So I'm going at the same time to concentrate more on semiconductor lasers. I would like to start my talk with a poem from Iranian poet say that look inside the teeniest of particle, you will find a universe inside. So if I start by periodic table and to look inside the atom of hydrogen, that we have one electron and one proton. So the most important achievement of the last century was to understand the structure of atoms, and you understood that the movement of the electron can create the photon, and this photon energy is related to the final and the initial energy level of the electron. So the most important part of understanding the structure of atom, it was the understanding the semiconductor. So what is the semiconductor? If I take only a part of semiconductor, colon 4, that we have carbon, silicon, and at the same time, colon 3 and 5, or 2 and 6, the last energy level, put that to become 3 and 5 to 8. And if I do the atomic and gap engineering of these binary, ternary, quaternaries of the different element, I can create the light, the lasers from deep UV up to triers, or the absorption detector from deep UV up to the peptides. So how I can make that the most important achievement of the last century to make it possible, it was to have the three things. One part, the support, the bulk crystal growth, that it was by Chokralski. On the other hand, it was by the epitaxy. It means that how to take to the susceptor and to put all of this atom on that, and with the photolithography. And if we combine with the quantum mechanic, we learn that if we use only the bulk crystal growth, bulk material, the density of a state as function of the energy will be parabolic. So if I make the device lasers or detector, is not going to be very efficient. But if I use the epitaxy and to make the quantum well superlattice density of a state, it becomes the stable behavior. I have one-dimensional confinement. And if I combine with the photolithography to have the quantum wire or quantum dots, in this case, I can have much better confinement, and the device that I'm making is going to be much more efficient. So last century, we understood the structure of atom, and this century, we try to create artificial atom. Last century, we understood the structure of molecule. This century, we try to create the artificial molecule. So the artificial atom and artificial molecule revolutionized our information technology by helping us to make nanosensor, nanomachine, a smart material, with the adjustable viscosity, density, elasticity, and etc. That the 1991, the dean of Northwestern, they sent that this picture to me, and he came 2 times to Thompson, and that they said that they fill up the lake, and just they said if they build this building, they were building, and they said if I accept, they are going to give me the last floor of the this building. So it was the driving force, and I started to build this facility, and my vision was for long term, and it's after 29 years, thanks to the pandemic, now everybody can understand what was my vision and how this kind of the facility that I put together is adapted for any time and for any application. So it was that I created the Center for Quantum Device, that's 29 years ago, and is a multidisciplinary, and that is, we are doing for all of the optoelectronic device, we do first the theory, and the design. After that material elaboration, we go to the characterization, optical, electrical, structural, and the device processing, measurement up to the system. Again, I will like to say that for this kind of activity, when I went to Thompson after my PhD, I was fascinated by semiconductor lasers. But when I came to Northwestern, I became fascinated by the artificial or focal planaries. So that is this facility that I put together can create exactly as you can see here, one part that is the first the camera that we created in the 3.5, and at the same time, the laser, the quantum cascade laser, and the system that I'm going to give you some detail later on. But for that, I try to create the undergraduate and graduate of solid-state engineering. I have to tell you that I didn't accept any administration responsibility, so I wanted to concentrate on the vision that I had, and you are going to see that what I did and what we are going to do. So that I created the 12 courses at the same time, and parallel the 4 textbook that the first edition of the fundamental of solid-state engineering that came out, that they are very at the same time popular. So for that, I explained to you now what I did and the inauguration of the center, that it was 1993 with von Klitzing and Leozaki, and that what we do and we did, we are doing, and is going to continue to manipulate and to do atomic and gap engineering, mostly 3.5 semiconductor, from deep UV up to terahertz, everything that is related to the lasers, detector, and of course transistor is part of that. Why mostly 3.5 semiconductor? Because 3.5, they have one part covalent bonding. At the same time, they are direct energy gap, and they have the zinc plant the symmetry. So that make that excellent for especially for the semiconductor lasers. But at the same time, if I come to the column 4, the carbon and silicon, we know that they are, unfortunately, they are indirect gap, and at the same time, they are diamond structure. So I am going to explain how we can combine all of this material together as a final system. So for that, I will start first by UV part. So in all of the talk that I'm giving, exactly as I explained before, for everything, at any device, first we do the theory, after that material growth, characterization, optical, structural, fabrication, measurement, and up to the system. So for UV, first we have to understand why the UV is important, because again, as I mentioned, for me, my driving force is always to find the application, why is useful and why we have to do. Ozone between 280 and 320 nanometer is opaque. So if we want to do telecommunication above ozone and to have the information about as an example, the space, the situational awareness, or the astronomy, etc., we need to have very high performance optoelectronic in UV. So for that, what we can do, again, as I mentioned, if I take only column 3 and column 5, by putting the aluminum, gallium, indium from the column 3, and by combining with the atom of the nitrogen column 5, I can come and to make the optoelectronic device from deep UV up to tris. But for that, but unfortunately in this system, the symmetry structure is Wurtz-Salt. So that's what I need. First, I need to have, again, the theory and background to say that how I can make it. Is the energy gap as function of lattice parameter. You have here aluminum nitride, gallium nitride, indium nitride, binary material, and at the same time ternary, quaternary combined. So I can come from the deep UV 200 nanometer up to infrared, and by intersubband, I can go up to terahertz. But for that, what I need the support. Unfortunately, for this material, I have not any substrate support that is lattice matched to this material. So the best one that I can use is sapphire substrate or the silicon. So I use sapphire because it's Wurtz-Salt, and at the same time large, the we can have excellent quality substrate. So I have now I have the epitaxy. So I created and I developed the system of the MOCVD, this reactor, with extra 1993 exclusively for this material, and still I'm using the same reactor, and still all of the result that we did and we are doing is coming from this reactor. I want here only to show you one thing. We have here sapphire substrate, and we are growing aluminum nitride on sapphire substrate. First of all, you have to know any material that you are growing, the growth temperature has to be at least 2/3 of the melting point of the crystal that you are using. So here the growth has to be at least at 1000 degrees. So every 9 plane of the sapphire 1 is corresponded to the 8 plane of aluminum nitride. But as you can see, every 9 plane, I have 1 edge dislocation. And after that, there is no defect. So that is the perfection. And you can see that at the same time here, atomic force microscope show that really I can have the perfect material. And that is done at the same time at Northwestern by Professor Dravid, and I love so much this result that I put at the same time on the cover of one of my book for the trinitrile. That is the perfection at the same time. So by using that, we try to grow the material from the aluminum nitride to 100 nanometer by increasing a little gallium in the aluminum nitride, and cook up to the gallium nitride, and after that to increase indium in gallium nitride up to the again indium nitride. You can see that we can create, that's the photoluminescence, but we did at the same time LED. We can have any wavelength that we want, and at the same time, not only for the laser, at the same time for the detector, and by doing inter-subband, we can go up to the terahertz. So here, as you can see, of course, the structure always is very complicated, is not simple, because we have to do the design in order to have the maximum confinement and to eliminate at the same time the defect. So it becomes very common. But by this kind of a structure, we can make the detector, that is the world first demonstration at the same time, and still they are the best, and still they are the active project everywhere in the world, especially in US at the same time. And as we can see here, responsivity as function of wavelength for changing a little composition, increasing in aluminum nitride, they get a little the gallium to aluminum nitride. We can have the detector for any wavelength that we want. So all of that is very, and my student that he did this work at this time, Daniel Walker, she's the vice president of Global GE. So after that, by doing that, we tried to come again with the application for the first, again, biological and chemical sensing. It means that we did each different LEDs for the different wavelength, and at the same time detector associated to that. If I take only 280 nanometer for the, if I shine a few molecules of anthrax, I can create the fluorescence, and at the same time with the detector, I can detect a few molecules of anthrax from the far. That it was at the time when we started, it was the time that anthrax was very, very important, and that we did that. It was from DARPA, the contract that we had for that. But today, we know that for the coronavirus, one of the elements for the eliminate that again is the UV is approximately, we don't know exactly, but we know that is less than 230 nanometer. So if we can find again now the efficient UV LEDs or lasers and to find the fluorescence associated to anthrax, we can again to detect the anthrax. That is the very active project at the present time. So now if I'm coming immediately, we did at the same time. That is the lasers, gallium indium oxide, gallium nitride, that is the 20 years ago. If you remember, it was very hot. The first lasers, blue lasers, is done by Nakamura in Nishio 1993. Finally, he got at the same time the Nobel Prize for that. And that the next one in the world, it was from Northwestern, from my group, with the excellent performance. But It was not that. As I mentioned, with this material, we can go up to terahash. So by doing the superlatives and to do the theory calculation, we demonstrated again, here is the intersub-band and that symptom transition and all of that. It was for the first time in the world, the result that you can see here, and that we can go again up to terahash. Why this material is important? Because with the difference, the wavelength, again, in order to make the longer wavelength, especially the quantum cascade or the terahash, we need to have the resonance tunneling, because that is based to the transport and the tunneling. That is the word first, again, the resonance tunneling in gallium nitride, gallium aluminum nitride that we did. And at the same time, at room temperature and liquid nitrogen, we tried to do 50 times and to show that that is stable. Why I'm telling that, for some of you that you are not familiar for that, you have to understand that is very, very sensitive to the dislocation. And as we have not the lattice match substrate, we have at least 10 to the 8, 10 to the 9 dislocation per square centimeter that can really eliminate the RTD, but by using the gallium nitride substrate or the lateral epitaxial overgrowth to remove the defect, we demonstrated that is possible. So in summary of the trinitride based from deep UV up to terahash, we have demonstrated intersub-band transition ranging from 1 to 6 micron with aluminum gallium nitride superlatives, and we have engineered double barrier gallium nitride resonance tunneling diode and achieve reliable and reproducible room temperature negative diffraction resistance. And this demonstration motivate toward realization of gallium nitride based QCL by intersub-band engineering and tunneling transport mechanism. And in addition, engineered gallium nitride RTD can be used for electronic oscillators in realization of electronic terahash emitter. That is the very, very, at the same time, the hot subject, and the Japanese, they are working a lot on that, but that is the future again. So another things that I mentioned to you, one, it was the sapphire set, but at the same time, the silicon. Why silicon? Silicon is a gift of God for the semiconductor. Why? Because first of all, we can make very fat mechanically, is very, very strong. And at the same time, we have two dielectric, silicon nitride and silicon oxide, that is perfectly lattice matched to silicon. So that is excellent for any kind of the device that we want to do. So that we developed the lateral epitaxial overgrowth of gallium nitride, aluminum nitride on silicon, and we demonstrated excellent at the same time the LED detector on all of that, and that again is a very hot subject and is continuing. So now, as I explained to you, aluminum nitride can go up to 6 electron volt. But at the same time, for this material, we have not lattice match substrate. So there is another possibility, gallium oxide. And gallium oxide has, again, for one part, unfortunately, is polymorph. It means that as you can see, the symmetry is not zinc blend, so that's a lower symmetry, but that is the direct bond gap material, and at the same time, large bond gap, and the high breakdown the field, and at the same time, this material we can make the substrate excellent lattice match to gallium oxide beta phase, and we can make N-top or the semi-insulating. One of the problem of this material, similar to the gallium nitride at the beginning, nobody can make p-top in this material. So just 2 years ago, they came and they asked me to be involved. So by emissivity, I tried immediately to put the water with the gallium, and we tried to demonstrate excellent at the same time performance, the transistor p-top. But I found that the silicon can play the amphoteric behavior to have the p-top. So we demonstrated the p-top transistor at the same time, and that is the very important subject at the present time. So for the highlight of the trinitride, I would like to say that we started 1993 with the aluminum nitride. Everything that you can see in the aluminum nitride, gallium aluminum nitride, is developed in my group at Northwestern, and at the same time, and is continuing at this time, and at the present time, we are doing at the same time the short wavelength, the APD, the single photon detector for many different applications, and the arrays, and that is continuing. So now let me to go to the other part of the 800, 980 nanometer of the of this visible spectrum. That again, it was since 60, 70 years, everybody, all of the group working, but in gallium arsenide, gallium aluminum arsenide, and the lasers, and the laser based on the aluminum gallium arsenide, it was not reliable, and the price of the high power laser was very expensive because that is the laser that we are using for the pump at the same time. So I developed the gallium free, aluminum free quaternary with MOCVD, and that revolutionized at the same time the technology of the high power, brought the price from the 1,000 per day per watt to the less than $1. And all of the information is in my book, MOCVD Challenge Volume 2, so I'm not going to speak about that. But if we go to the another range, 1.3, 1.5 micron range, for the telecommunication, again, as you know, that is the 50, 60 years, everybody working, especially for the silica optical fiber, and that, but unfortunately, they were using liquid phase epitaxy, and it was impossible to have high performance, and especially the DFB. So I developed the MOCVD at Thomson exclusively for this material, and that it revolutionized the technology of the silica optical fiber, and that it was during 10 years at Thomson, we were only one in the world to produce this kind of lasers, and that all of the information, everything is in my book, MOCVD Challenge Volume 1, and at the same time now is the second edition. You have to know that this picture, exactly as you can see, that is the world first indium phosphide, gallium indium arsenide, super lattice that I did. So all of the two-dimensional electron gas, two-dimensional whole gas, quantum, everything based that, and at the same time, all of the result that I'm going to show you for the quantum cascade, again, or for the detector, is based on technology that I developed at Northwestern. So now I'm going to the, again, infrared. Infrared, again, mostly on the laser part. Why? Because, again, competing with the Nobel Prize, the Gerard, that he tried to come with the high power laser that is showing, and I'm showing at the same time what we can do with the semiconductor lasers. So for that, why? For the 3 to 300 micron, again, using indium phosphide, indium gallium arsenide, indium aluminum arsenide by material that I developed at Thomson, again, for the 1.3, 1.5 micron lasers. So why, first of all, is important? Because for the wavelength, any molecule has a vibration molecule, has an energy that equivalent of that for the detection, for the spectroscopy, everything. We need to have a equivalent lasers. So for the difference application, we need the laser in any wavelength. So how we can do that? There are two ways that we can do. We can do that at the same time with the interband and using the electron and hole. So that is nice, as I explained to you. But when we go for the infrared, unfortunately, this energy gap, it becomes very small near the KT, so we cannot make the reliable device. So what is the other solution is intersubband. Intersubband, when Leozaki gave the ideas of the super lattice, but the Kazarinov and Suri, they came with the ideas of the making the lasers in that many different groups they were involved of that, and the first injection came from Bell Labs, but after that it was in my group that we developed again the result that I'm going to show you. That's, as I'm telling, it was a tool at Bell Labs. I make it a product. So what we do for that, that is the unipolar again, and by gap engineering for any wavelength, we do the gap engineering, we do the waveguide modeling, we do the thermal analysis, and after that, again, that is the most important part. Theory, everybody can do, that's a material. We have the theory, as I explained to you. After that, we need now the substrate is clear, we have the indium phosphide, is great. But what we can do for the epitaxy, that it was that I developed this reactor, that is the gas source molecular beam epitaxy, is the mixture of the MBE and MOCVD. So I use that for the active layers, and at the same time, MOCVD reactor for the iron doped, and at the same time for the buffer and the top layer, by combining all of that, and at the same time the processing, all of that, it was the things that I developed in France, and I use it again for the quantum cascade at Northwestern, and by that we come with that. Again, I have to tell you, because that's the 1997 that Durvasula from DARPA and Henry Everett from Army, that they were supporting us, me, and at the same time Federico for the Intercept, and me for the interband antimonite for the infrared 3.5 micron. They came in March 1997. They asked me, they want me to be involved. So immediately, end of the March, the April, we had this result. Why? Because exactly as I mentioned, in the reactor that I had, I was doing this material for the QUIP, for the quantum well infrared photodetector. So immediately we tried to put that and to calculate, and that is exactly, as you can see, the 170. But during and immediately the same year, 3 months later, we published, and that it was in Photonic, that it was the publicity about the room temperature, high power, the 8.5. So during 5 years, my group was only one in the world to have for the difference wavelength, high power, continuous wave, more than 100, and I was giving to Jerry Mayer at NRL. He was measuring, and he was going to the government, and finally he succeeded to convince the DARPA to put 2 big programs of the EMIL and ELPAS. So, but now I would like to give you some of the important highlight of this material and the things that we are doing and the continuation. Again, I would like to explain to you one thing. As I'm telling to my group all the time, everything that I'm telling you for the 3-5 optoelectronic, it is, and is continued to be always the material and the device of the day, and everybody needs is like air and oxygen. Now I come here to the high power, high wall plug efficiency, continuous room temperature, because we have to have that in order that industry can use it. For that, 2011, we came to have the high performance at 5 micron mid wavelength with the 21% wall plug efficiency at continuous at room temperature, and at 105 degrees C, still we had 2.41 watt continuous wave with the wall plug efficiency of 9.3. Of course, nobody can believe, so I gave it to them, again, the daylight solution, and they measured, and they said that the daylight solution, that is the Northwestern, that is the daylight measurement, they said that the results are in good agreement with Northwestern for power efficiency, voltage, and wall plug efficiency. Daylight measure 5.67 watts versus 4.8 watts of Northwestern. Why? Because everything that I'm doing and I'm publishing, I take the very low level, not the best result. So that at this time, since 2011, nobody in the world, despite that the best group in the world working on this material, couldn't come to break this record, updated till last year. The Navy gave again another contract to us, to my group, for the for the wall plug efficiency. So immediately we record and we break the record. Again, the 4 paper that you can see, all of that is published this year, came out, and we came for the wall plug efficiency 31% in pulse, 22% in continuous wave, and at the same time with the 5.6 watt. Something that is very important. I have to tell you that from the 5 millimeter cavity length, 12 watts in continuous wave is coming out with the wall plug efficiency of 41%, of course, at liquid nitrogen, but that 12 watts coming out from the facet, that is unbelievable result. So that is it means that that's the product to use in industry. Now, is the high power, but we need at the same time, for many applications, then we need single mode high power, high wall plug efficiency, continuous wave room temperature. So we came, that is the world first, again, DFB, with the 2.4 watts continuous wave, 10% wall plug efficiency, single mode. But now we went to the photonic crystals. We make the photonic crystal distributed feedback at 4.4 micron. With 34 watts, broad area emitter with near diffraction limited beam quality, 34 watts of peak power with the narrow emission spectra, far field and emitting spectra. But to make photonic crystal is very difficult, so we try to make it much simpler. By that, we came with the world highest power crucial application of an angled cavity. For this angled Fabry Pro that we can do, we tilted the angle about 12 degrees, that is for 4.85 micron, and the ridge width is only 300 micron, and the cavity length 5.8 millimeter. Back facet is HR coated, front facet is AR coated. A room temperature output of 203 watts is obtained, which is the highest for any quantum cascade laser or any diode. The wall plug efficiency is 10%, and the far field single lobed at the facet normal direction, and the full width at half maximum angle of the far field is only 3 degrees, which is the 2 times of the diffraction limit. So now coming to the surface emitting, because for many applications we need surface emitting. That is the world first surface emitting QCL at approximately 4.8 micron continuous wave single mode, but the is not the fundamental mode. So for fundamental mode, we came with the doing the surface grating with the lateral grating, and to have the simulation far field experimental result, and we can have here the pulse mode, the peak. We have 1.5 watt output power for the ring of the 400. That is the highest power that we can have for the ring lasers. And now the gain for the master oscillator power amplifier for the high power single mode room temperature at the any wavelength from the short up to the long wavelength. Again, as I explained, we have to have high power continuous wave and at the same time single mode. So that is the MOPA. Both the power and efficiency are the highest for single quantum cascade laser emitter at 3.8, 4.6, 8 micron wavelength range, and all the device emit in single mode in the working current with single lobed far field distribution. This result is just, I believe that it just published. So now we need not only high power single mode, but we need at the same time the tuning. The tuning, why the tuning is important for the difference application. So in order to come to the tuning, we try to use sample grading, and with the sample grading 1 and sample grading 2, we try to use at the same time the amplifier. With that, we do the master oscillator power amplifier that was created from a sample grading DFB QCL with an integrated amplifier. And for that, we demonstrated the wide electrical tuning of 300 nanometer in pulse with the more than 5 watts of the peak power over much of the 300 nanometer, but we did at the same time continuous wave with electrical tuning of 120 centimeter wide with the 1.25 again the output power in continuous wave with the good side mode suppression ratio of 20 dB and the beam quality observed in all amplifier current. That's the result that you can see. Monolithic, widely tunable QCL between 6 to 9.5. The wavelength tunable lasers beam is from 6 to 9.5 from a single emitter feature, and is realized by integrating 8 sample grating laser arrays with, again, an on-chip beam combiner, 8 to 4, 4 to 2, 2 to 1, and a compact and user-friendly system is built around the laser source for random wavelength access and rapid scan up to 1 kilohertz, any wavelength that we want. So that is the unique, again, beautiful and unique in the world. Now, going to the first high power tunable surface emitting quantum cascade laser with a stable output beam. exactly as you can see again, we have the sample grading DFB1, sample grading DFB2, and the amplifier that is the low-cost alternative for high-power QCL using angled outcoupler for surface emission. We don't need to have any cleaving of the surface, no cliff facet required for the laser operation, and the near diffraction limited output which has no string with emission wavelength, and the all electrical single mode tuning up to 200 nanometer demonstrated an on-chip optical amplification with the peak output power higher than 6 watt over entire tuning range. So this result is just published, and now we are going to the photonic integrated circuit. We need that block the ROIC and the LSI. We need all of the photonic active and passive to be on the same chip and to have the monolithic steering with surface emitting for the different application. That is again world first demonstration of monolithic the steering with the surface emitting quantum cascade lasers. As you can see here, the widest steering of the 17.9 degree of any laser based on a grating out coupler, thanks to wide monolithic wavelength tuning larger than 200 nanometer, and integrated grating heater we have here for fine adjustment of the angle at a given output wavelength, and steering can be done very rapidly with a measured of 3 dB bandwidths of 7.75 kilohertz output beam in single lobe, and very narrow 0.5 to 0.6 with the full width of maximum, and with no external optic is required. So now I would like to go to the silicon photonic. Exactly as I mentioned, we would like to put everything on silicon, and at the same time we need high power phase locked QCL based on optical phase arrays for to have 2-3 dimensional at the same time the steering. So for that, the challenge is to have single wavelength output with fixed phase profile at output, and targeting 3 different range: short, mid, and long. So here you have world first 16 element single mode phase lock QCL arrays. We have the DFB grating, we have MMI splitter, and we have the laser waveguide. That all of that is formed by plasma etching. The device has 3 sections. We have the DFB base, we have MMI splitter, that the 2 to 4, 4 to 8, and 8 to 16, and we have at the same time AR coating with the angled facet termination in order to eliminate any reflectivity. Here we have reflectivity as function of angle for this laser 4.8 micron with the anti-reflecting coating using yttrium oxide, and as we can see with the 4th degree, the angled facet, the reflectivity is less than 0.1%. So the result of that is here. For the 8 micron, we have 51 watts single mode phase locked. For 4.8 micron, we have 30 watts single mode phase locked. For 3.8 micron, we have 20 watts single mode phase locked. So all of that is the world first, but is in parts. Now, in order to having continuous wave, here we having continuous wave, world the highest, long wavelength, continuous wave power, phase locked QCL arrays. A 6 millimeter distributed feedback laser OPA emits at 8 to 8.2 watts with the threshold current density only 1.8 kiloampere and wall plug efficiency of 9.5% in continuous wave at room temperature. Single spectrum phase locked with the exactly as you can see here at 8.1 mark for the far field is achieved. The spectral line width is only 1.2 nanometer, which is limited by our resolution of our FTIR, and at the same time the far field is only 0.25 degree, which is limited by the pitch size and the reach width. So now let me to go to the last part, the teraise. The teraise is very important. Why? Because for the different reason, enable many useful application in medical, security, sensing, and communication. It passed through the clothes, ceramic, without that. But why? We know all of that since long time. But what we need to make it useful, we need the room temperature, high power diode, semiconductor diode that work in teraise. So that it was, again, by using the QCL or result, and at the same time, nonlinearity in the QCL, we know that if we use by optimizing the second order nonlinear susceptibility, we can have the teraise emission through different frequency generation. And at the same time, if we optimize the third order nonlinear susceptibility, we can have frequency come through 4-bit mixing. So we did that, and here is the result. World first high power to enable teraise QCL, and that is the world highest teraise power, 1.9 milliwatt, from a room temperature monolithic device. And at the same time, the forfeit is only 12.5 degree, and we have the single mode teraise emission from 1 to 4.6 teraise from arrays of the teraise, the DFG, the QCL, and we have the world first monolithic continuous wave teraise tuning from 2 to 4.6 was achieved using a sample grading DFB DBR design. And that I have to say that one of the most important part, if we look in the emitting spectra at the 4 teraise, as function of temperature, as function of injection current, we have no change of the emitting spectra. That is for telecommunication. For the many application is excellent because it's that based on the DFG. Not the same way for the frequency comb. Again, we tried the frequency comb. We demonstrated high power, excellent performance, quantum, the frequency comb from the 3-4 micron up to 10-11, but that is the world first room temperature teraise QCL frequency comb that we just published in Nature Communication, and it becomes the highlight at the same time of Nature Photonic. So for that, I would like to say that when we started again in 1997, it was the first, thanks to the control of the material. Of course, you have to know the theory, you have to know the physics, but after that is a control of the material. Everything that you can see here is the record, and that the new result is not there, is not here, and is continuing again. But it's not only the problem of the publication, the problem of the love testing, this kind of result over 1 watt at 100 degrees C in continuous wave with the power cycling over 30 minutes, there is no degradation. We demonstrated we sent a publication, Applied Physics Letters last week. If we have the material without defect, and if we have the processing without defect, this kind of laser at 1 watt continuous wave room temperature can work more than 1 million hours, similar to the indium phosphide-based lasers that I put in my book, MOCVD Challenge, is exactly the same performance. So now, the last part of my talk, I would like to say that everything that we do in lasers, we can do in the detector, because the structure is the forward bias, you have laser, but the reverse bias, you have the detector. But at the same time, you cannot have, for any information technology, we need the photon, the laser, to create the photon, to bring the information far. And after that, we need the detector to absorb that, associated again to same wavelength, and we need the transistor for the data analysis. Exactly as mentioned, again, I repeat, when I went to Thompson, I was fascinated by semiconductor laser, but when I went to Northwestern, my dream was the focal planaries artificial eyes. And that, unfortunately, everything related to the focal planaries that is classified and is big company and never coming to the university. Now, nobody could believe that at university is possible to make the focal planaries, but I did it. So I'm coming that from the deep UV again up to teraise. Faith we went today, I came again only the 3.5. One part, the top 2, the mercury cadmium telluride, it was the material of choice at the time, and still, and since 50, 60 years, more than 60, 70 billion per year is go for the focal planaries based on top 2. But I'm not going to the detail of the problem, so I came with the 3-5. All of the, again, colon 3, colon 5, all of the indium antimonide, indium azide antimonide, indium with the thallium bismuth antimonide, top 2, and at the same time. So first coming to the short wavelength. That is the world first 280 nanometer the UV focal planaries, that it was important at the time that we did, because it was very important for the anthrax, and that was the contract that we had from DARPA, and still at this time, my group is the pioneering. We have much better result, and today we are doing for the shorter wavelength again, as I mentioned, single photon detector, shorter wavelength arrays for the different application, especially, again, I am saying that's one of the things for the anthrax, for the coronavirus at the same time. So now we are going to the longer wavelength. How we can do with the atomic engineering, gap engineering of the 2 gallium antimonide and indium arsenide, because that is very interesting material. Conduction band of indium arsenide is lower than valence band of gallium antimonide. So when we put together for the electron combined in indium arsenide and hold in the gallium antimonide, so they are separated. But when we put that as a thin layer super lattice, and we put the minimum of the conduction and valence band is in the center of brilliance, so it behaves like a phase one. So by one monolayer change we can change the energy gap from the deep UV that we did for 4 the nanometer that work that we are doing at this time for NASA, up to the 32 and the terahertz. So, but the beauty is that, again, if you look at here, by inserting only 1 2 monolayer aluminum antimonide, I can increase the gap, and by that we can have that. So by that, the 1997, these ideas of the top 2 superlatives came by Leo Szilárd, and he did with the MBE at the IBM in his lab, but all of the different group was working. Of course, when the Nobel Prize working on that, everybody working, and that nobody could make the focal planaries. So they came to me, and in 2003, for the first time, I make the focal planaries in the top 2, and of course that is the my patent at the same time. And that after that we continue, and it was interesting because all of the result that I have is always thanks to one of the genius program manager that they have a division, and here it was the really for the laser it was Durvasula and Henry Everett, and for that at the same Henry Temkin, and here at the same time it was the Mehmet Tidro that he had. After that, one after each other, we did one after each other the different kind of the different kind of focal planaries, and all of the everything is transferred through my student to the government, to the country, and at the same time now everywhere they are working, and they put in United States VISTA program, and that at the same time, if I look the timeline of the antimonide base, you can see that the first investigation of the antimonide from the first day that I developed the inauguration of my center at Northwestern, all of that you can see is the first and the demonstration, and it's continuing at this time. We have a few very important projects that we are working and going on. So by that, I would like to conclude my talk to say that a wide range of material and device technology has been explored with the wavelength ranging from the 200 nanometer to 300 micron. Each wavelength range has a unique challenge and a long history of accomplishment. Mid-infrared and TRIS technology have recently seen tremendous expansion thanks to the development of new quantum cascade laser architecture and unprecedented power and efficiency, power scaling, electrical wavelength tuning, frequency comb generation, and surface emission have all been demonstrated and are now being integrated. It will soon be possible to construct systems with allow access to sources from multi-spectral region on a common platform and in a monolithic integration, and this will enable development of new system concepts which represent the future of optoelectronics. And exactly as I mentioned, more from the deep UV and the terrace. That is the range, and to eliminate all of the gap, to bring the two together again with the mimicking the nature. It means that to the quanta as small as possible, as efficient as possible. And by that, I would like to say that what does the future hold? Exactly as you can see here, to put everything. Why not? If we go to the carbon, we know that we got already 2 Nobel Prize on the carbon. But again, I would like to finish to say that for the optoelectronic, for the lasers, again, as I explained, and detector that I showed, that the 3,5 was, is, and continue to be the salt of the food, and carbon, and at the same time, silicon, they are the food. I have to acknowledge the support, interest, and encouragement of the many of my great program managers in the different government, and at the same time, none of this result that I presented and we are doing, it's possible without the excellent work of the genius student, postdoc, research faculty, and of course the administration at Northwestern. But nothing, I have to say, Thomson CSF. Why? Because I learned semiconductor at Thomson Central Research Lab. But unfortunately, when I left, Central Research Lab is closed, and Thomson changed the name to put Thales. So for that, I would like to thank organizing committee, and especially again to congratulate Professor Gérard Moreau for the having Nobel Prize in Physics for high power laser that he did, and he perfectly deserved it. Have a great day, and I hope next time you are not going to be bothered by coronavirus. It means that all of the research that we are doing, I hope that we are going to have to find rapidly a solution, not only to detect rapidly the coronavirus or any future virus, but at the same time to find the solution for to eliminate it as soon as possible. Thanks.